So, in chapter 17, this is what I'm going to summarize some stuff we've been talking about, all right? We have probabilities. We're looking for probabilities. They're giving us information. It's asking us to find certain things. So they're going to ask you questions like, how many coin flips are there going to be until you get the first heads? What's the probability that I get the first coin flip on the fourth flip? What's the probability that I get 4 heads when I flip a coin out of 7 flips, like coin flips? Those types of questions we're answering. Okay? With a lot of stuff going on, so I put it all together in the same kind of mindset. In this case, we don't have probability models like we did in chapter 16. So when it starts asking about expected value for means and standard deviations, so far things we've learned this year, we can find mean and standard deviation when we have a list of data, right? We don't have any lists of data in this class, like right in this chapter. We can find mean and standard deviation if we have a probability model like a table, but we don't have a table in this chapter. So we're back to where we have a geometric model or a binomial model. So if it's asking you for the mean or standard deviation, you have to assess what they're asking you. Are they asking you how many coin flips you would expect to get before the first heads? Or are they just asking you how many coin flips you would how many heads you would expect in a certain amount of coin flips? Those are 2 different questions, 2 different models. The standard deviation would go along with that. So, geometric is always the first something. You're looking for the first brunette in a group of 20 people. You're looking for the first brunette. What's the 6th person that walks through the door? But always the first. With binomial, you're not talking about that anymore. Binomial, you're talking about a certain amount in a certain set of trials. Okay, so I want to know the number of brunettes that are in a group of 20 people. I want to know what the probability is there's exactly 3 brunettes in a group of 20 people. I want to know the probability there's at least 7 brunettes in a group of 20 people. So not multiple people. We couldn't answer these questions in previous chapters because we didn't have the tools to do so. And these were defining a number of trials that we're using. Before, it was like open-ended almost. But now I have a specific set number of things. Okay? Yes? Maybe? So I'm going to go through the assignment from last night and help you answer some questions. Number 16, everyone in this room should have been able to do because it was all about stuff we've done before. It was geometric stuff. 18 and 20, you should be able to do parts of, and you should have been able to attempt other parts of, but maybe not. Before we get started, I'm going to pass out the binomial calculator sheet, and we'll talk about it when we get there. Okay? You have the geometric one, I'll give you the binomial one.
Wait, can we still go like
All right, so I kind of showed you the binomial calculator stuff yesterday, sort of. But I didn't show you everything. Yesterday we talked about geometric PDF and CDF. We also have a binomial PDF and CDF, and we'll talk about those when we get there. Okay? Let's do 16 first. Okay, these are the ones you should be able to do. About 8% of males are colorblind, and a researcher needs some colorblind subjects for an experiment and begins checking potential subjects. On average, how many men should the researcher expect to check to find one who is colorblind? So it's like finding the first one that is colorblind. That's why we're using geometric. So how do you find an average for geometric? 1 over the probability, and in this case, we're looking for someone that is colorblind. So 1 over 0.08, which is 12.5. So I would expect the researcher to have to see 12.5 or 12 men 13 men before finding one that's colorblind. That's what that means. Are we get that? What's the probability behind and the first 4 men she checks? So the first 4, not colorblind. So how do I find that? For the 4, there's 4 men. We're not finding any colorblind among the first 4. So colorblind was 0.08, so not colorblind is 0.92. So that's 0.7164. So far, so good? On C, what's the probability that the first colorblind man found will be the 6th person? First is going to be on the 6th person. So that's geometric. You can do it by hand because geometric ones aren't hard, or you can do it in your calculator. I will do it both ways. If you're doing it by hand, that means you don't have anybody that's colorblind the first 5, and you have someone that's colorblind on the 6th, or you're going to use geometric model in the calculator, or you're going to use PDF or CDF. PDF, you're finding a specific outcome. CDF stands for cumulative, so that's adding things. PDF finds a specific, the first person is on this trial. So, we would do 0.92 to the 5th times 0.08, that's one possibility. Or you use geometric PDF. We have a probability of getting a colorblind person as 0.08, and we're trying to find if it happens on the 6th person. They're the same probability, 0.053. Questions about how to do C? Does that make sense? Do we know the difference between PDF and CDF? What's the probability that you find someone who is colorblind before checking the 10th man? So that means you find the first one in the first 9 people, because it says before the 10th. So you could, by hand, have to add up all those probabilities, right? It would be like 0.08 plus 0.92 times 0.08 and yada, 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 yada. Right? That's a lot of people. A lot of things. Or you could use what? Geometric, PDF or CDF? CDF, because we're adding a bunch of stuff together. So cumulative. So CDF, like on C. We use PDF for questions like C, where it's like exactly this trial. CDF, where we're doing adding a bunch of stuff up. So this would be the same thing. 0.08 is probably the colorblind. We still are doing, let's see here, up to 9 people. And it's going to add this together for us, 0.528. Questions on 16? How'd you do on 16? Does 16 make sense though? That's just like we did 2 days ago, right? Just geometric. It's asking for the first something on every question. Mm-hmm. You? Okay. So let's look at 18 and 20 then. Some of these are geometric and some of them are binomial. So you have to recognize which ones use which, where. That doesn't make any sense. An Olympic archer is able to hit the bullseye 80% of the time. Assume each shot is independent of the others. That's just telling you that we have Bernoulli trials. We have 2 outcomes, miss or hits, and it says they're independent. If she shoots 6 arrows, what's the probability of each of the following results? So, first one, A. Her first bullseye comes on the 3rd arrow. Is that geometric or binomial? Geometric. First bullseye on the third arrow. So if we were doing that by hand, that means she misses the first two. So it's probably the missing one. So 0.2 squared times 0.8. If you were going to use the calculator, which you really don't have to in this case, would you use PDF or CDF? PDF, because you're doing the first one on a specific trial. Excellent. So that ends up being 0.032. Yes, good. Okay. B, I think, is the most confusing one in the whole list. So look it all the way down. So she misses the bullseye at least once. So first of all, is this geometric or binomial? It's binomial. It's not saying anything about first anything. Right? We're not trying to, it says at least once. That means she can miss 1, 2, 3, or 4, 5, or 4 or 5 or 6 times, right? When we did at least in chapter 14, what do we say about at least? 1 minus the complement, right? If it says she misses at least once, that means she can miss once, twice, 3 times, 4 times, 5 times, or 6 times. You could add all those together. Or you could do 1 minus she misses 0. Right, 1 minus no misses. It says she's going to miss at least once. So she could miss 1, 2, 3, 4, 5, 6 times. So we're doing no misses. Yes, but no. Since we're doing binomial, let's try to do some things in the calculator so you don't mess this up. Remember, it would be 0.8, or sorry, we're doing no misses, right? So she would do 0.2.
Wait, no misses would mean she made.
And there's two ways to do this. It's the same thing, but different numbers. No misses, or you can do all hits. Remember, binomial has that formula involving the combinations, right? Yeah, not geometric where it's super simple. I'm not meaning this is complicated. I'm just thinking, make sure you think it through. When you're using binomial, you're supposed to use that formula, but there's combinations of things. So, in your calculator, this would be a good time to discuss binomial. There is also a binomial PDF and CDF function in your calculator. Okay? Yes? PDF does the same thing that geometric PDF does. It is for a specific trial, a specific number of successes in a certain amount of trials. So if it said on D, it's going to say she gets exactly 4 bullseyes, that's going to be something we would use PDF for. CDF is going to add them up. It's going to add up from the bottom. So it's going to add up 0, 1, 2, 3, 4, 5, 6, whatever you put the number in, it's going to add from 0 to that number. Okay? So, in this case, we're doing 1 minus no misses. So if I want to do this in the calculator, just for example's sake, we have to do since it's no misses, that means you're getting all hits, right? So that means we're going to use CDF.
Wait, so how many trials?
There's 6 arrows. 6 arrows. If we're doing, let's make sure we're all on the same page. I'm doing all hits. Okay. So if she's hitting them all, that means the percent of hitting a bullseye is 0.8. And then that's how many that she gets out of 6. So in this, all hits is 6. Oh, we shouldn't have used CDF. That's why, because that would be all of them. That would have cumulative add them all together. We're doing all hits. That means she gets 6 in 6. Exactly. Right? CDF would have done 0, 1, 2, 3, 4, 5, 6. That's why you got 1. That makes complete sense why we got 1, because it adds them all together. So we're going to use CDF, PDF. I keep saying CDF. Yeah, PDF will give you exactly what you want. Exactly 6 in 6. So 0.262 . 0.262 So 1 minus 0.262. If you did no misses,
Wait, so you subtract that from 1.
yeah, you subtract that from 1. If you did no misses, you don't get the same answer, but when you do PDF, you would do 6 trials. What's the probability of missing? 0.2, and she's going to miss 0 times. You should get the same number, 0.262. That's why I was making sure we're all on the same page while doing misses and hits. The probabilities are different, and the number we're doing is different. But you get the same probability. Okay. At least ones are always the most confusing, right? Yes, the answer is 0.738. Now, on the other ones that we do later, it won't be this complicated, I promise. But again, PDF is when you want exactly something to happen, and CDF is a cumulative. So when we did CDF by accident a second ago, you got 1. Well, that makes sense, because if you have 6 trials, and you put in that you want 6 successes for CDF, it's going to add up. You had 0, 1, 2, 3, 4, 5, and 6. So that's all of them, which should have equaled 1, right? Okay. On C, her first bullseye comes on the 4th or 5th arrow. Is that geometric or binomial? Geometric, first bullseye. Now, geometric CDF adds stuff together, but it doesn't add just 2 together, you just feel like it. It adds 0, 1, 2, 3, 4, as an order, okay? So you need to do these separately and then add them together. So it would be that she gets it on the 4th time. Well, that means she misses the first 3 and then gets it on the 4th one. Yes. Or she misses on the first 4 and gets it on the 5th one. You could also do this by doing geometric PDF twice and add them together. Right. So second distribution, geometric PDF. We have 0.8 is our probability of getting a bullseye, and we want to get it on the 4th time, and then I add together the fact I get it on the 5th time, 0.00768. If you did it in the calculator, again, binomial and geometric questions ask different things, so you have to know which one to use in which scenario. You get the same thing if you did my hand. 0.0077. All right, questions on C. It's geometric because it says the first bullseye. That's geometric. Because it's on part B, it says she misses the bullseye at least once. It's something about the first anything. So it's binomial. On D, she gets exactly 4 bullseyes. Is that geometric or binomial? Binomial. You have 2 options. You can do the formula that involves combinations, or you can use your calculator, right? If you're going to use your calculator, which is what you probably do, you're probably not going to write the formula down. Then, because if you did, you'd write it down and just do it in your calculator anyway. So, she gets exactly 4 bullseyes, PDF or CDF. PDF. So, binomial, PDF. There's 6 arrows being shot. We get the bullseye 80% of the time, and we want to get it 4 bullseyes. So 0.246. The number P is their probability of success. So yeah, getting a bullseye. Is how many you want. Questions on D? On E, she gets at least 4 bullseyes. That's binomial. Okay, so there's 2 ways you can do this one. She gets at least 4. That means she gets 4, 5, or 6, right? So you can do PDF and do 4, and then 5, and then 6, and add them all together. Or you can do 1 minus the probability of getting 3 or less, which is what CDF does. Right, so you can do PDF by doing 4, 5, and 6 added together. Or you can do CDF by doing 1 minus the cumulative 0 through 3. So binom CDF, I still have 6 arrows. Getting a bullseye is still 80% of the time, and up to 3. And I would do 1 minus that. Or you would do binom PDF of 4 plus 5 plus 6. So at least 4, that's 4, 5, or 6, or 1 minus 3 or less. Questions about E? All right, on F, she gets at most 4 bullseyes. So binomial. Well, so she gets at most 4. That's 0, 1, 2, 3, or 4. So you can do them all individually and add them all together. But that's what CDF does. It does 0 up to a number, right? So we can just do CDF for that one. Yeah, up to 4. So CDF, again, 6 arrows. You might get bullseye 80% of the time. Up to 4 of them. 0.3446. 4. Is this better? We're getting it together. Questions on 18. Do you know how to figure out if it's binomial or geometric? Do you understand the calculator functions a little bit better? Okay. On 20, consider our archer from exercise 18. How many bullseyes do you expect her to get? Is that a binomial question or a geometric question? Geometric. No. Binomial. It doesn't say anything about how many she expects to get before the first bullseye. Because how many bullseyes do you expect her to get? That's multiple, right? Geometric is always talking about 1, the first one. So the mean, and it should make sense, if you know how many you expect her to get, you take the probability of getting a bullseye and multiply it by how many arrows she's shooting. So 6 times 0.8, which is 4.8. So you expect her to get 4.8 bullseyes. Yeah. Questions about A, why it's binomial? In B, it says with what standard deviation? The standard deviation is the square root of n times p times q. Q being whatever the complement of 0.8 is. So 6 times 0.8 times 0.2, and that ends up being 0.98. So far, so good? On C, it says if she keeps shooting arrows until she hits the bullseye, how long do you expect it to take? That is a geometric question. How long does it take until she hits the first bullseye? So that's mean is 1 over p. So that's 1 over 0.8, which is 1.25. questions. This is making it better. So, especially with the mean questions, like I said earlier, you don't have data, so you can't take an average like you normally would. You don't have a table, so you can't find an expected value like you normally would. So if you're doing an expected value in this case, you have to determine what model you're using. It's geometric if it's how many until the first something happens, and it's binomial if it's how many you expect to get out of however many trials you have. Questions? All right, then let's finish the chapter up real fast. Okay? Now, what if you have really large numbers? Because that's the problem. So here it talks about the Tennessee Red Cross, and it says they have a need for at least 1,850 units of O negative blood this year, and it estimates it'll collect blood from 32,000 donors. And apparently the probability of success is 0.06. This is that equation for binomial, and there is no way your calculator can compute that. It's too many digits. Look, it has, the first term has more than 100,000 digits. Your calculator cannot do it. So what do you do when you have these large sizes for your sample? No, doing it by hand is not going to help. So we need to know what to do when there's these large sample sizes. So when we're dealing with this large number of trials, making direct calculations is tedious, but the normal model comes to the rescue. You can find the mean and standard deviation. You can calculate that, NP and the square root of NPQ. If you have a mean and standard deviation, then you can make a normal model, right? We talked about that even though in chapter 6 we weren't calling them that, when we find areas under the curve, those are just probabilities, right? So it turns out to be a very good approximation for the binomial model. Okay? So we're going to put that into practice. Now, we have to know how large enough is. How do we know we have enough trials to be able to use it? Because when you have a small set of trials, this doesn't work. But if you have a large set of trials, it will. So we have this success-failure condition. You can only use a normal model if you expect at least 10 successes and 10 failures. So NP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. So if you only have a trial size of 15, this can't happen anyway. If you have a trial size of 20, it's not guaranteed to happen then. Unless it was half and half, which is highly unlikely. So we have to look at trials and make sure that each of the successes and failures is greater than 10. So I'm going to do one problem. Okay? The archer in exercise 18 will be shooting 200 arrows in a large competition. What are the mean and standard deviation of the number of bullseyes she might get? So we're using geometric or binomial? Binomial. So number should we expect her to get? So the mean is n times p. So that's 200 times making the bullseye still 0.8. So that's 160. So we expect her to get 160 bullseyes. Yes? The standard deviation is the square root of n times p times q. So 200 times 0.8 times 0.2, that's 5.67. You guys could have done that last night, no big deal. Mean standard deviation. On part B, it says, is a normal model appropriate here? Well, how are we going to know if we can use a normal model approximation or not? What did we just talk about? Yeah, you'd have 10 successes and 10 failures. So NP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. Well, NP is 160, so that works. And if that was 160, then the other one has to be 40, right? So they're both greater than 10, so we can use a normal model. Success failure condition is met, we can use one. Is that okay with everybody? On C, it says use the 68, 95, 99.7 rule to describe the distribution of the number of bullseyes she may get. That should ring some bells. So you got to draw the model. We have the mean, right? 160. We know the standard deviation. We just add 5.7 each time. I was rounding, who knows? So what does that 68, 95, 99.7 situation mean? 68% what? The middle part. What does the middle part mean? Right, the one standard deviation, right? Which my model is not good. That should take up way more space. And then 95 would be 2 standard deviations. And 3 is 99.7. And this is the number of bullseyes, right? So on D, would you be surprised if she made only 140 bullseyes? Yeah, that's like over here and below. But what would your explanation be? Well, how are you going to explain it statistically? How are you going to explain your surprise? Why are you surprised? It's greater than 3 standard deviations away from the mean, right? So it's highly unlikely. If you're trying to find the actual probability, you could use normal CDF. Right? We can find a probability that way. That's going from negative infinity to 140 with a mean of 160 and a standard deviation of 5.7. So the probability is 0.0002, which makes sense. If this middle part is 99.7 and it's 0.997, so there's only 0.003% left to split between the two halves. Negative infinity to 140. So you would say something about it being less than 3 standard deviations away from the mean, or you could say something about how it's only this probability that it could happen, that kind of thing. 140.